Okay, good morning. Yeah, let's get started. So today what we're going to do is we have two separate lectures and one tutorial, right? So the first lecture we're continuing from yesterday. We looked at different elements, why they are important, what they do for plants. We looked at nitrogen, phosphorus, potassium, looked at calcium, looked at magnesium, right, sulfur and micronutrients. We just learned about different things, about different elements. You also did some hands-on activities identifying some deficiencies, right? Some of them are very easy, some of them are kind of there, some of them are difficult, right? So you have a key, you can keep that key with you, it's a very useful thing, right? That's a nice thing, especially what I want you to do. I know you are going tomorrow, is it tomorrow, to a tour, you may be visiting a greenhouse. So all those concepts you learned about light, temperature, water, substrates, nutrients, look for those things in the greenhouse. Okay, what are they doing in real world? Is it same, different? You don't have to advise them because they also have their experience, right? But try to note down, and probably when I come back, on the first tutorial on the 6th or sometime, we can talk about it. You can bring some questions back. Maybe you can ask them if you can take pictures. If they say okay, you can take pictures of whatever it is and bring those questions back. I can upload all those pictures and then we can look at those questions and I can answer those questions also. Okay. Also pay attention to greenhouse structure. I haven't discussed that, but the topics that we talk as soon as I come back are on greenhouse construction, structure, things like that. So pay attention to the structure. Okay, things like that. Take some pictures, whatever you want. If you have any doubt, grab a picture and then we can discuss here. But utilize the trip, just not like a fun trip, right? You're going there on a scientific trip. So go there and ask yourself with the background information you have, see what is going on there. Don't challenge the people there, okay? It won't look nice. But get that information and then we can discuss here, all right? But if they come forward and say, do you have a suggestion for us? Maybe you can tell them at that point. So be gentle, that's all, okay? But in any case, that's a different thing. You do that tomorrow. But then we'll continue today the second topic on nutrition, which is about EC and pH. Quite applied, like we always do. We learn something about the environmental variable that we are discussing, and then we look into applied aspects of that. So today is the applied aspects. The second lecture is going to be also very applied. It's on plant growth regulation. It is mostly useful in floriculture industry, but we are also, greenhouse production also involves floriculture, not just vegetables. So both are included in greenhouses. I mean, actually not just vegetables, fruits also included, right? Blueberries, strawberries, tomatoes, peppers, and then leafy greens, and then you have all floricultural crops. So we will also, if you have noticed here and there, I've been talking about floricultural crops. Soilless substrates mostly used for, of course, floriculture crops and also for vegetables, right? But this second one I'm going to talk today, plant growth regulation, is mostly for floriculture industry, all right? And then we'll do pour through ECPH measurements today. He's arranging for ECPH meter, and I think Dr. Anjush is bringing some parts, so we can probably just step outside and then we can do pour through measurements there, okay? And I'll show you how to do that. All right, that's good. So let's start with EC and pH. Who can tell me what EC letters stand for? Electrical conductivity, okay? And pH is, what is the definition of pH? Of hydrogen concentration, right? Okay, good. Now let's look into this little bit more details here. So I want to explain the concept of EC here on this slide. So let's focus on this cartoon first. So here is a beaker with pure water. You got two electrodes, right? Cathode and anode, all right? And then you put a small current meter, an ammeter or something like, or a voltmeter, whatever you want. You put it there and then you measure it. You will see some current going through, a little bit, not too much. Pure water is a poor conductor of electricity. It does conduct, but it's a poor conductor of electricity. Okay, you see some current going through. You can see electron flow and current flow over there. Okay, but then in that same beaker, you take a little fertilizer, a spoon of the fertilizer, and then you add the fertilizer. Mix it a little bit. What happens? All those ions become soluble. They are now floating freely in the solution, right? As soon as you do that, immediately what you will notice is, here there was a small current, but here you will see a big current going through. The meter now goes like that. So what is the difference now? There was not much of a current flow here in the pure water, but with ions, fertilizer ions soluble here, you are seeing a lot of current going through. What's happening here is that all those ions, they are helping in carrying electrons. They are helping in conductivity, ionic conductivity. Okay, so ions help in conductivity. The moment they are dissolved in solution, they help in electron flow, and that's why you see a lot of current going through. So what is this telling us? You can see a lot of current flow when there are a lot of ions in the solution. When there are less amount of ions, there is less current flow. When there are more ions in the solution, there is more current flow. Therefore, you can, if you can measure the current flow, by measuring the current flow or conductivity, right, electrical conductivity, you can measure the concentration of ions in the solution, right. There is a linear relationship between how much current or conductivity is happening and then concentration of all the ions in that solution. That is what we are interested in, right? We want to know the concentration of fertilizer. You can send it to laboratory, run through some chemical analysis, that's all complicated. But here is a simple technique where you put, a sensor with 2 electrodes, and then you measure the voltage and current, whatever it is, and get an electrical conductivity value, and that number is proportional to the concentration of ions. Fertilizer ions are also non-fertilizer ions, and that's something I'm going to get to in the next slide, but it is going to measure the concentration of all dissolved ions in that solution. It makes the job easy, and that's why it's a very popular measurement. It's a very simple measurement, and it's a very popular measurement. Okay, but there are certain things, considerations you should keep in mind when you are working with electrical conductivity. You understand the concept, right? The EC concept, why EC is important. But there are considerations. Number one consideration is, the point I want to emphasize is that whatever ion conducts electricity is included in that measurement. That ion could be a fertilizer ion. It also can be a non-fertilizer ion. Let's say you have hard water with you. You know hard water? If you have hard water and if you are taking a shower, it's hard to get rid of the soap, right, with the hard water. But hard water contains bicarbonates, calcium and magnesium bicarbonates already dissolved in it. Carbonates also are ions, CO3 minus. But plants don't need carbonates, isn't it? They don't take carbonates. Did I tell you on those 14 elements that we talked about, was carbonate an element? No. But it is in the solution because it is a part of the water, and it is also helping in electrical conductivity. So if your water has a lot of certain non-fertilizer ions, like in this case bicarbonates, you are not only measuring the concentration of fertilizer, but you are also measuring the concentration of non-fertilizer ions in the solution. So you may think, so when I say, okay, EC is good, as long as EC is 1.5 or 2.0, the crop is getting all the fertilizer it wants. And then you take that word from me, and then you are measuring EC, and you see all the time 2.0, good, there is a lot of fertilizer for the plants. But maybe that number 2.0 is heavily dominated by those bicarbonates. They are influencing that number. If that is the case, you are actually supplying plants with less fertilizer. Although you are seeing a good number, that number is coming from what? Non-fertilizer and bicarbonate. So this is important. There is also, and so what we normally tell people is, before, if I give you a recommendation, let's say 2.0, and we'll talk about units in a second. If I give a recommendation at 2.0 EC is good for crops, first what you need to do is you have to take your plain water, the water that you use in irrigation, whether it is tap water, well water, whatever water it is. Take that water without any fertilizer in it, measure the EC. If that fertilizer, most likely you will see an EC of 0.75 to even close to 1.0. That is coming from what? Non-fertilizer ions. We have not added any fertilizer in that water yet, but still there is a number there. Then what you need to do is, okay, if it is, let's say 1.0, now what is your recommendation? Your recommendation is 2.0, but now you have to add 2.0 to what? That 1.0 and increase your EC to 3.0 for your plants. Now that's one point. Keep in mind, EC measures both fertilizer and non-fertilizer ions. The other problem with EC is, it's a measure of all concentration of all ions together. It will not tell you how much nitrogen or nitrates are there, phosphates are there, or any other elements are there. It tells you the total of all ions. So what is the problem with that? The problem is this. If you are doing something like hydroponics, where you have a big tank and you are continuously recirculating, yesterday you saw some NFT systems, maybe tomorrow you will see some of the NFT systems out there, and we'll talk more on hydroponics. But if you are recirculating, recycling solution all the time, plants are like us, they have some favorite nutrients. You see, some of the nutrients are consumed quickly, that's called luxury consumption. They take nitrates and some even potassium, except for a few, 2 or 3, most of the elements are taken, but they are taken at different rates. Some elements are taken rapidly by plants, they remove them from the solution. Some elements are taken slowly by roots, by plants, and some are taken really, really slowly. So if this is the scenario, if plants are taking nutrients at different rates, what happens after a few days of continuously recirculating the solution? The solution gets depleted with some nutrients which are taken rapidly, right? Because plants like them, so they are being taken rapidly. Over a period of 7-8 days, that particular nutrient is more in the plant than in the solution. Okay, so its concentration is now lower. While those that are taken at a slower rate, their concentration will still be higher. And then most importantly, those bicarbonates which are never taken, they keep on accumulating. Because whenever you see the water level going down in the tank, you add water. And what does that water contain? More bicarbonates. You also add a little bit of fertilizer. You measure the EC and then you add a little bit of fertilizer. But the thing is, on day 1, the solution is a balanced one. You carefully prepared it. But as the time goes on, the composition of that fertilizer solution is changing. And what is changing that? Plants. They take nutrients the way they like. Some nutrients are taken more faster, some are taken more slower. So now when you are measuring EC and you are just thinking that 2.0 is good, the first day the 2.0 is coming from maybe a lot of nitrogen, phosphorus and potassium. Maybe on the 10th day, it may be coming more from bicarbonates and some other slowly taken nutrients. Now let's go back to yesterday's class. If there is some nitrogen deficiency, you will start seeing what? Stunted growth, yellow ink, potassium deficiency, phosphorus deficiency, So now you are facing this challenge with EC. If you simply rely on EC number, thinking that maintaining a healthy EC number is more than enough, there could be situations, and especially in hydroponic culture, where you may not be supplying the optimum amount of some of those major nutrients that plants really take rapidly. Okay, you should keep that in mind. Okay, EC is measure of all of them. It does not tell you the concentration of a single element. That's the reason why what we recommend in hydroponics is, don't continuously recycle the same solution. After some time, you may have to throw it away. Use it in the field or throw it away, prepare a fresh solution. Or get a sample, run it through laboratory if you have a laboratory close by, and measure the concentration of elements. You may want to do that in 1 or 2 cycles. Then once you have the data with you, now you know what happens in your case and you can probably adjust it. But once you send the sample to the laboratory guys will tell you how much of nitrates are there, phosphates are there. Compare those numbers with the first day composition. And if you see big difference, then you know, okay, we have to, in a month of time, we may have to change the solution and add back more nitrates, more phosphates, things like that. If you do that one time, then after that, it is kind of the similar situation. After every month, you may want to top off more of calcium nitrate or more of some other specific fertilizer that is getting depleted faster. Okay. But again, keep in mind, EC is sum total of all elements, not one or two. Okay. And EC can also measure non-fertilizer ions. As long as your water is good quality, you don't have any of those bicarbonates in it, you are in good shape. But if you have that, most likely then you will end up with accumulation of them, and with time those accumulated non-fertilizer ions starts influencing the EC value, and whatever you are measuring, that EC value is an apparent EC value. It is probably not reflecting the original concentration that you supplied to plants on the day one. Okay. Does this make sense with respect to EC, the problem with EC? Okay. There is something else I also want to mention with EC. EC is a good indicator of nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. What are we missing there? Look at these. What are we missing? Micronutrients. Why is EC not a so good indicator of micronutrients? Because? Why? Yes. We add a tiny bit of micronutrients, so their ion constant is so less. These are the most dominant ions. So EC is a good measure of macronutrients. If you are really into micronutrients and you want to measure those concentration, you may be not using this EC measurement. You have to probably use something else. Okay. Now let's talk about units. Electrical conductivity is measured in Siemens, capital S, Siemens. Okay. Conductivity is inverse of resistivity. Okay. Conduction, resistance, these are all related, inverse of that. But the thing is this, the thing is, when you are using an EC meter, maybe this afternoon we'll see that, you will see all kinds of units. I want to tell you that 1 millis, again look at EC is measured in Siemens, but it's actually measured in Siemens per centimeter, per length. In the next slide I'll tell you why it is. So the units for EC are Siemens per some unit length. So if it is millisiemens, then it is centimeters. If it is decisiemens, D stands for deci. Decisiemens, it's meters. Or if it is microsiemens, it is also centimeter. But look at that. 1 millisiemen per centimeter is nothing but 1 decisiemen per meter, which is equals to 1000 microsiemens per centimeter. So if you have a EC meter, most likely this afternoon when we see that EC meter, we may see in this range, 1500, 2000. What that means is, in terms of decisiemens, it's 1.5 or 2.0. Same goes with millisiemens too. Remember this, 1 millisiemen per centimeter is same as 1 decisiemens per meter is same as 1000 microsiemens. Often in scientific publications or also with recommendations, we use either these two. This is the SI unit. If you are writing a paper, this is the SI unit, decisiemens per meter. And all the recommendations I am telling you, 2.0, 1.5, they are all based on that or this, but based on that. Okay. So units for EC, EC considerations, the things you need to know, and then a definition of EC so far. Okay, theory behind EC. All right, so let's look at some of the EC sensors. This is one EC sensor. More recently, we've been using this EC sensor. These are some of the older ones. HANA probes are, from the other company. This is also HANA probe, but there are many other companies in addition to that. But there are some sensors, and I want to explain a little bit in very general sense how these sensors work. Okay. For EC measurement, you need electrodes, right? 2 electrodes, right? Those 2 electrodes are right there in that bulb down here. That is the probe. This is the meter. Look at this meter. It's giving you not just the EC. It can also give you pH also. In this case, it's set to pH right now. You are seeing pH. But these meters, it gives you pH, EC, and also total dissolvable solids too. Okay. You can also get the temperature measurement. You can change it to Fahrenheit or Celsius, whatever you want. So there is the probe is right down there. In that probe, you'll have electrodes. Okay. The bulb is probably one of the electrodes, and inside there is a small sort of like a metal wire or something, that will be another electrode. That's how they create these electrodes right in that bulb. So if that bulb breaks, the meter is gone. So you got to be very, very careful. Okay. Always what happens is you have to cover this portion of the probe. It comes with a cap. Okay, it comes with a cap. You want to make sure that you add a little bit of water, a good quality of water, into that cap and close that. You don't want to leave the EC probe open. It is going to affect its calibration, it's going to affect its life, and most importantly, you may end up breaking that bulb. Okay, so always cover it with a cap that comes with it, but you have to add a little bit of water. Keep it moist always. Those electrodes should remain moist for long longevity. Okay. All right. So how does this EC meter work? What is the basic principle? Sorry. What is the principle? So in all these EC meters, again, what are we interested in measuring? We are measuring electrical conductivity. Instead of conductivity, we measure the reciprocal of that, the resistance, and then we invert it. Okay. So the concept is electrical conductivity is measured by calculating resistance between electrodes. There are two electrodes, the current is flowing through. We can measure the resistance of the flow of the current, and from that we can inverse it and we can get electrical conductivity. As simple as that. Okay. Here is a formula for that. EC is Siemens per centimeter. 1 over R is that resistance, that is R is resistance in ohms, and we also need to know a couple more things, L and S. L is the length of that electrode and S is the area of that electrode. Once you know these things, but by the way, you don't need to even worry about any of these things. This is how the company, the manufacturer, estimates EC for you. Okay, you will get EC values directly in Siemens per or millisiemens per centimeter or Siemens per decisiemens per meter. But here is a little bit of concept here, how that whole sensor is operating. It measures resistance and then it also measures, these two are constant for any sensor. The length of the probe and the area is constant, and so they plug in those numbers. They use Ohm's law. Actually, if you are into electricity and physics, they use Ohm's law. They measure voltage. From voltage, they measure resistance. V is equals to IR, right? Ohm's law. Is that what it is? Yes. Or R is equals to V by I. So we measure, good morning, we measure voltage and we measure current, and from that we get resistance, and from resistance you get conductivity. But don't worry too much about that. All you need to know is, look at now this equation. This is resistance 1 over R. That becomes Siemens when Siemens is 1 over R. But length by area gives per unit length. See, this is centimeter. This is centimeter square. So you get centimeter to the power of minus 1 or 1 over centimeter. That's why it is Siemens per centimeter. Okay. But in any case, don't worry too much about this. This is only to show you how that EC sensors look. Some of the EC sensors, older ones, are like, tabletop. You may get 2 electrodes and you have to take this far and then put this. They're all there. But the more, I probably will show you another. Yesterday, do you remember I showed you a probe? It was for water content. I said it uses dielectric permittivity and it had 2 rods, about that much. And there was another one that was like 10 centimeters. Those also measure EC. Just 2 rods, you dip it into it. There are all kinds of sensors. There are all kinds of sensors. If you go on Amazon, you may find something as cheap as $30, $40, all the way up to these HANA probes are approximately $350 or $400. Yeah, probably something like close to 20,000 rupees here in the US. So, but the key thing is, what are those bottles? You read the number, 1413 microsiemens. Yeah, those are standards. Those are standards, and very, very important. Always remember this rule. A sensor is only as good as its calibration. If you don't calibrate your sensors, you are just looking at some random numbers. That's all. Those numbers mean nothing. You should calibrate a sensor. If not, that number is all just a random number. It can be anything. You can come up with a number with your, and say this is what it is. That's all. That's how good it is. So calibrate your sensors. And EC calibration, what we call 1-point calibration. Okay. We just use a standard solution or powder, or they also sell these in pouches. You don't have to buy a bottle, they sell in pouches. Okay. I think I have a slide on calibration, but I can explain now because we are talking about it. Basically, 1413 microsiemens per centimeter. What is that in terms of decisiemens? 1.413. So you take your EC probe, okay, and you put your EC probe. Now you don't want to put into that bottle. If you do that, you are polluting that standard. You want to take a small beaker, pour that good solution into that beaker, and put your EC probe into it. And if the EC probe is within 5%, it will never read exactly that what the standard is. Okay, but if it is within 5%, its calibration is good. Otherwise, you have to adjust some. There are some buttons on it, or in terms of electrical things, you can actually change the mode to calibration and press some of the buttons and change the numbers. You can type in some numbers, increase or decrease it, or you can adjust it with a screwdriver in older ones. But you have to calibrate. Then the question comes, how often you should calibrate? I would recommend, people do at least, I've known commercial operations where they at least do once a month, but even if it's a very simple thing, if you can do at least twice a month, it'd be good actually. You won't see much of a difference, but at least make sure you do once a month, okay? Within 5%, make sure that it is adjusted, okay? You can do that. You can do that. By the way, in most of the greenhouses, hydroponic greenhouses, it's a continuous EC measurement, right? Inflow. And so what, maybe when I talk about hydroponics, I will talk about that. We maintain ABC tank system, 3 separate tanks. Each tank has a different fertilizer. And then as the water is coming through, fertilizer water is coming through, we measure EC instantaneously. And if the EC is lower than what you want, automatically it is dosed, right? That is different. So in such situations, it may be very useful to calibrate more often. But unless you are a researcher and you are doing an experiment, every day calibration is probably not required because you won't probably find much of a difference. Well, I don't know how valuable it is, but I will tell you something about temperature in a minute. You have to keep in mind that all these EC sensors are affected by temperature. Now, the measurement that you get, whatever the calibration that you're looking at, all that resistance calculations and the output voltage, that is highly sensitive to the temperature. Usually it is done around for 20 or 25 degrees Celsius at the manufacturer site, okay? But when you are making a measurement at, let's say, 30 degrees Celsius, then you get a higher value than what is exact. So it's like, it's confounding basically. The temperature is confounding it, and you are getting a wrong number simply because the measurement, the water temperature is higher than what the company originally did the calibration for. So, however, most modern EC sensors are temperature compensated. Remember yesterday I said pressure compensated emitters? What do pressure compensated emitters? They adjust for pressure, right? But like the same way, the EC sensors that you get, for example, that one over there is temperature compensated. So that is the reason why it's measuring temperature. There is a good reason why this EC meter also measures temperature, because it uses that number and adjusts the EC value automatically for you. Okay, it adjusts that EC value for the laboratory calibration, and that is why it measures the temperature. So it is automatically adjusting the EC value for us. The older meters are not temperature compensated. Maybe those you may want to warm up to a certain, I don't know, whatever that number is, but generally it is not recommended to increase the temperature because the sensor itself does that. These are temperature compensated probes. Both EC and pH probes are temperature compensated. Temperature has a direct effect on measurement and all these sensors. And that's the reason why modern newer versions of the sensors automatically measure temperature and adjust the measurement for whatever the temperature is. Okay, all right. You understand now? Okay. All right. All right. You saw that one. Let's talk about. There are two types of EC measurements. One is solution EC. The other is substrate EC. Rather, one is fertilizer solution EC. The other is substrate EC. Okay. So the first one, fertilizer solution EC, is something that you supply to plants. Is the fertilizer solution, the EC of the fertilizer solution you supply to plants. Let's say you have a tank and you may have fertilizer solution in the tank that you are supplying to plants. The EC of that fertilizer solution is the fertilizer solution. It's a liquid one. Okay. Of course, it's all liquid, but that's fertilizer solution. You see, is what we supply to plants. But more important is not what you supply to plants. The more important is what is surrounding the root zone, in the substrate, in the soil. You may supply 2.0, but it may be 3.0 surrounding the plants. Yesterday I talked about what? Sub-irrigation. What does sub-irrigation do? It accumulates fertilizer. There is no leaching. So you may be supplying 1.0 fertilizer solution, but the substrate may be at 3.0 because it's accumulating with time. That 3.0 affects plant growth, not what you are supplying. So substrate EC is more important than solution EC. Remember that. Okay. In hydroponics, the story is slightly different. It's the same solution going through recycling. So it's all solution EC. But in floriculture, in container production, in vegetable production, peppers, tomatoes, you should be measuring substrate EC. There are two ways you can measure substrate EC. One, through these direct probes. Here is a substrate EC probe. You see the probe? It's got a metal pointed tip. That is where you measure EC. Those are the electrodes. Okay, that's where you got the electrodes. But it is protected. Why? You are inserting that probe into substrate, and therefore you want to make sure that those electrodes are protected. They're not like a glass bulb that breaks. So you are inserting it. So that's why these are directly in situ probes. As soon as you put this probe into the substrate, you get a value. Okay.
So why measuring substrate EC is important?
Okay, let's go back. So it's important to ask questions. If you are not following, please ask the question. So let's say you are providing a fertilizer to plants and it has got an EC of 1.0 decisiemens per meter. Okay, that's a recommendation. You send that to plants and you are adding, where are you adding that fertilizer? You are adding to the soil or to the substrate. Now, as soon as you supply that, plants are taking some, but they are not taking all of the nutrients. What is happening to the nutrients that are not taken by the plants? They are accumulating in the substrate, right? You keep on adding this fertilizer every day. It's only 1.0 there, but because the nutrients are accumulating in the substrate, with time what happens to that number? Will it be 1.0 or more than 1.0? It can be one more or it can also be less. We don't know the situation. If plants take more than you are supplying, it will be less. If plants take less than what you are supplying, it will accumulate, it will be more. But which number is actually affecting plant growth? Is what you are supplying or is what is there surrounding the roots? The one that is surrounding the roots. Because that's what roots are saying. That is called substrate EC. What roots are seeing is substrate EC. What you are supplying is your fertilizer solution EC. Now tell me which one is more important.
So nearby roots, but substrate. So this substrate EC affects what is the EC in the solution there in the nearby roots?
Of course, so when I say substrate EC, I'm actually talking about the ions dissolved in the substrate. So remember, going back, I thought you would connect that to your pore space and solution. Let me explain a little bit more. Think of substrate. What does substrate has got solid particles, okay, and it's got pores, right? And inside pores, what do you have? Solution, and in that solution, what is there? Ions are dissolved. So when you insert this probe, you are measuring the concentration of ions in that solution which is residing in the pores.
I was thinking about actual medium like cocoa bean.
Yeah, but let me get to that. I was about to get to that, but it's a good question. Remember, that's what it is measuring there. Here you are measuring in pure solution, but there you are measuring in the pores. However, that's why we got two methods here. But this one, this probe, it measures what we call bulk substrate EC, bulk substrate EC. So what it is measuring is, it's definitely measuring the ions in that pores, the solution in the pores. That's very, very important. That's what roots are saying. But in addition to that, that number is also affected by two more things: air in the substrate, and also the solid particles also a little bit affect that number. It's all electricity. It's all electromagnetic radiation, and they're all going to affect that number. So bulk EC, the advantage is very quick. You insert the probe and you get a number, but that number is generally going to be less than actually what is there in the pores, slightly less than what is there in the pores, because the solution in the pores has higher EC, whereas the other two things, the air and substrate, they're going to lower that number slightly. That's the reason why the bulk EC is slightly less than what is exactly there in the pore solution. Okay, but the advantage of that is you insert the probe and you get a quick number, so you don't have to worry about the other process that we do this afternoon, pour through, which I'm going to explain in the next slide, is the right one, but it's a little bit more cumbersome. It takes some time. Okay, so you can measure exactly the concentration of ions in the pores. That's called pore water conductivity. Okay, just the solution in the pores, you can do that. But if you don't want to get to the cumbersome level, and you will see how cumbersome it is in the next slide, you can just insert a probe and get a quick number, which is called bulk substrate EC. So pore water EC, bulk substrate EC. I think you are not following it, right? Where am I missing you? Go back.
Yes, sir, I was actually thinking, let's say, I mean, basic only. Let's say EC is high.
Okay.
EC affects transportation of ions to the plant.
Right.
So high EC, will that not mean plants are having more ions to transport?
If you have more ions, what happens? I told you osmotic stress. Do you remember that? What is that osmotic stress? Can anybody tell me what that osmotic stress is and what does it do to plants?
So when the concentration of the ions increases in the substrate or in the soil, the plants are unable to take water from the soil, and it ultimately results in the building or any.
With time. Remember that big cartoon you draw with the plants? I think you were drawing it, right? I think you both were doing it. In the soil, what I was giving you numbers like minus 0.1 in the soil. But if you have too much of the fertilizer there, that will become from minus 0.1 to minus 0.7. And then the water can't get into the root. So you got to make sure that you maintain optimum values. Okay, it's not like you can add all of that fertilizer and the plants can take whatever they want. No, it's not correct. Okay, but that's okay. But then going back, there are two types of EC substrate EC measurements. One is a bulk measurement, the other is a pore water measurement. I want you to remember these two: a bulk measurement and a pore water measurement. So what is the difference? Pore water measurement is the concentration of ions in the substrate pores. There is a solution, right, in the substrate pores. In that solution, you have all these ions dissolved. That is what pore water EC, and that is what roots are saying exactly. Okay, but this sensor, of course, 85 to 90% of the reading that you get from the sensor is affected by that pore water EC. Good, but it also gets measurements from the air and also the solid particles. The air and solid particles EC, the contribution is lower than what is there in the pore water. So the overall value is going to be less when you use the bulk measurement. Okay, so that's bulk measurement. Then the pore water measurement or pore water conductivity, I'm going to explain to you in the next slide how to get that. But again, keep in mind, there are two types of EC measurements. One is you are measuring the fertilizer solution you are supplying to plants. That's in the tank. It has nothing to do with the soil or substrate. It's in the tank. You are mixing it every day. You are sending it to plants. The other is in the substrate itself. The one in the substrate matters because that's what the plant's roots see. Within that substrate, you got two types. One is pore water and the other is bulk EC. Bulk EC is what the sensors measure. Pore water is what I'm going to talk about in a slightly different way. Okay. you can use this leachate collection method, which is also called as pour through method, which is what we will do this afternoon. Hopefully, if you can give us some parts, we will do that. That is pore water EC measurement. Or you can also use direct estimation probes like this to measure bulk EC measurement. Both are related to substrates, not to the fertilizer solution you're supplying. Okay, but you can also do this is what you can do in your facility, in your farm. But if you don't have all these facilities, you don't have sensors, probes, you don't have people to do that, you can take soil and send it to a laboratory, and they also do the same EC measurements for you. They use methods called SME, saturated extract measure, or 1:2 method. Basically what they do is they take your substrate, they put it in a pot, they add a lot of water, in fact all the way to the top, 2 times water than to 1 part soil to 2 parts water, or they saturate the medium in that beaker and leave it aside overnight, 24 hours. And then they come back and they take a little bit of the solution at the top, and then they put the probe and measure. The concept there is that when you add that much water, all of the water in the pores and this get kind of equilibrated in the 24-hour period, and then you take a little sample and put a probe, you kind of know the pore water. But again, these numbers are still going to be lower. I have a slide where I compare different methods. The numbers I compare different. So that kind of clarifies a lot of things that you still have in your mind. But let me explain the other method, the pour through method. Again, we are dealing with substrate EC. We just talked about bulk EC measurement. Now we are going to go for pore water EC measurement. Okay. What is the advantage of bulk EC? Easy, easy and quick. Okay. But what is the disadvantage of that? Because it is also affected by air and soil. Okay. It also, keep in mind, it's not a bad number. 90% of that value is coming from pore water EC only, but there is a little bit more contribution from soil and air, and that's why it's a slightly lower number. But now let's get to that exactly pore water. How do we get? Inside the pore there is water, and in that water we have all the nutrients. That is what the roots are seeing. So how do we get that water out and measure EC? That's the procedure. Okay. So here is that pour through method. We want to try and do this afternoon with whatever we have. We may not have the exact situation, but we'll try to do that. Okay. So what you need to do is, in order to pour water measurement, you irrigate plants with whatever fertilizer water, whatever you do normally in the morning. Come in the morning, thoroughly irrigate. Irrigate close to container capacity. Whether it is fertilizer solution that normally use or water, whatever it is, usually with fertilizer solution, right? So thoroughly irrigate the plants. Let them sit for 1 hour. 1 hour. Don't do anything for 1 hour. During that 1 hour, all the fertilizer that you have applied will equilibrate inside the substrate. Roots will take whatever they want, and there will be some left, whatever is left over is there. That is kind of like what we call steady state. Okay. Then come back, put a small plastic saucer below the pot. You see that? You put a saucer, right? And just take a little bit of water, that same fertilizer water or tap water, that whatever you used in the morning, take a little bit of that and uniformly apply on top of the pot. You see, before this, you brought the pot to what? Container capacity. What is container capacity? And then what happens if you add more water on top? What happened yesterday? You were doing container capacity and you were measuring, isn't it? I think you measured it, and the number was all the time, whatever you pour back, it's coming down, right? Substrate cannot take any more. So when you add a little bit on the top uniformly, let's say another 100 milliliters, what happens to that? That fertilizer water that you are applying here, it goes down, right? When it is going down, what is it doing? It is pushing the water that is already in the substrate down, right? You have a pot, the substrate is at container capacity, it cannot take any more water, but you pour more water on top. This water is going down, gravity is pulling it down, but as it is going down, it is pushing the water that is already in the substrate down, down, down. So the water in the substrate comes out and gets collected in the saucer, whereas the water that you applied will stay in the substrate. Does it make sense? When you add a little bit more water at the top, the pot is at container capacity, it cannot take any more water. but you poured another 100 milliliters on top. This 100 milliliters is going down, and as it is going through the pores, it is pushing already the existing water in the pores down, right? It's not like it's going to accumulate at the top. What did you see yesterday when you were doing? You pour the water. Did you see the water at the top? No, the water is coming down at the bottom through the pores, through the gravity. But what is that water that is coming down and getting collected? Where is that water originally? It was inside in the pores, and that fertilizer water in the pores has ions in it. And isn't that what you want to really measure? That's what you are really interested, isn't it? You want to measure the concentration of ions that was in the pores, and here you are artificially pushing that pore water into the saucer. Once you collect in the saucer, put it in a beaker and put your probe, you get pore water EC and pH. You know, there is another simpler method. What people do, they bring the parts to container capacity. After half an hour or 1 hour, they come and they simply push on top of the substrate. What happens when you push it? You are compacting, and when you compact, you are closing the pores, and when pores get closed, the water gets collected in the saucer. That's also possible, but pour through is better. You have to apply a little bit at the top, and then you collect it. See this one? When we poured something like that, the brown color water is getting collected in the saucer. This brown color water is nothing but in the substrate that was in the pores. It contains all the salts, and you put it in a beaker and you measure it. Now you know the EC of the fertilizer concentration that is there inside the pores of the substrate. That is what the roots are seeing. That's called pour through method. Very popular, but how many steps are there? Different steps. It takes almost 2 hours to, or 1.5 hours to finish this. Let's say you have a big area, large number of parts. It takes a lot of time. Compare this with bulk EC measurement. You insert the probe, you get a number. Let's say you're growing peppers and tomatoes in big, peat bags or in the ground. You can't do this. The only way you can measure substrate is by that bulk probe. You insert the probe and you get a number. So there are pros and cons for everything. You have to use the method that fits to your situation. Okay, if you are growing plants in pots, maybe you can use pour through. Pour through, it gives you the accurate value, but you're not growing in pots, you're growing in big peat bags or in the ground. There's no way you can do this, so you use a sensor. Both methods. Okay, there are certain considerations even for pour through. That's what I'm showing you in the next slide. See here, this is how, let's say you have applied fertilizer. Okay, this blue color, this is water. Okay, I just put it like a cartoon for you. This blue color is water. Here is a part, you have a substrate, okay, and then you applied water. The part is at container capacity, and you got lots and lots of nutrients here, okay, in the substrate. Then you apply a little bit of water. The water that you are applying is shown in light blue color, and then the water that is already there in the pores is shown in dark blue color. Okay, so what's happening when you apply that? The new water is pushing down the old water into the saucer, and you collect it and you measure it. But let's say if you apply too much water, is it funny for you? Is it funny? I'm seeing you laughing. Please, I do not like people are laughing when I'm talking. Is it funny for you? What is funny? Why don't you share it with me? What's funny? Am I looking funny to you when I'm speaking? Why are you laughing? Why are you smiling? Please focus. I'm putting all of my time. Please don't laugh, smile, do this. I don't really like that. I want my students to focus, okay? 1, 2, 3 times. I've been watching for last 10 minutes. You've been laughing, smiling. Please don't do that. I really appreciate it if you don't do that, okay? All right, let's get back. So if you apply too much water, what's happening here? If you apply too much water, you are not only collecting the existing water, but you're also collecting what? The water that you applied. That's error. That's error. What is your intention? Your intention is to measure what is in the substrate, but your intention is not to measure what you are applying. So you got to make sure that you apply right amount of water. You don't want to apply too much water. If you apply too much water, you get a wrong number. This is the most important consideration for pour through. Okay, you will test that this afternoon. All right, so just keep that in mind. Don't want to do that. Okay, that's not correct. All right, so I said there are different methods, right? There is a dilution method, these two are laboratory methods. Here is a pour through method. Again, for pour through, keep in mind the number should be within 1.0 to 2.6 decisiemens per meter. This is the normal range for most of the crops. If you are below 1, kind of low, you are low. If you are in the range of 2.6 to 4.6, you are getting to that osmotic stress situation. It's bit higher. And 4.6 to 6.5, very high. You are stressing your plants. You're going to kill them if you do that continuously. Okay, some numbers for you. But again, keep in mind, the pour through is always slightly higher than the two laboratory methods where they really saturate the solution. And gives you a lower value. So just keep in mind, this is the range that you want to follow with pour through. You may get a slightly lower values for your bulk EC, but it won't be too low. Okay. All right, that's about EC. We talked about what is EC, what are the considerations, issues with EC. You know, you're going to measure the whole concentration. You will measure the concentration of non-fertilizer salts too. Keep that in mind. Okay, and then we looked at different methods of EC measurement. Fertilizer measurement is easy. You just put a probe and you get a number. But what is important is the substrate EC. It's important. And within substrate EC, you got two scenarios. You can use a sensor, you get a value. Or you can use a pour through measurement if you are growing in containers and get the pour water value too. Okay, bulk EC, pour water EC. Always focus on substrate EC. This is what matters. Don't totally rely on, I'm supplying fertilizer solutions, good quality, that's good for plants. No. Focus on substrate EC. Substrate EC is what matters. Okay. All right. Let's go from EC to pH. Okay. And I will say this before we talk about EC and pH. You may ask you, why are we learning about pH, right? So what does EC tell you? EC tells you the concentration of ions you are supplying to plants. But you know why pH is important? Now, pH will determine whether those ions will become soluble in that solution or not. So you may apply right amount of nutrients to plants, but what if they are not soluble? What if they are not in the solution for the roots to take? You still have a problem. So pH determines the solubility of those ions in that solution. That is why it's just not EC. You should also really focus on pH too. Unless you manage these two things, you are not providing proper nutrition in greenhouse crop production. Okay, and I have a very good slide that shows how pH affects different elements. But this is the reason why we are studying pH. pH influences nutrient availability. You may supply nutrients, but it doesn't mean that those nutrients are going to be available to plants as long as you maintain optimum pH for plants, they are not available. Okay, and you will see what that optimum pH is. But let's talk some basics about pH. pH scale can be from 0 to 14, okay, all the way. Anything less than 6, 6.5, we call it acidic. Neutrality is there around 7, 6.5, 7.5, and afterwards up to 7, 7.5. You don't want to even go beyond 7.5 for plants. It's too much right there. It's basic. Okay. So as you all know, pH is negative logarithm of hydrogen or hydronium ion concentration. So here is an example. Let's say you have the concentration of that hydronium is 0.001 moles per liter. So it's a concentration, right? That's how we measure concentration in chemistry. 0.001 moles per liter. The way you calculate pH is negative log 10 of that 0.001, which gives you minus of minus 3 becomes 3. That's how you get numbers. When I say pH of 3, 3.5, 4, that is the value calculated using concentration of that. But it is negative because it's always such a low number. Log of, if you are a mathematical guy, If you have Excel on your computer, so you can test it. Logarithm log 10 of point anything decimals is a negative number. So you got to have a negative over negative to make it positive, and that's why it's negative logarithm in the definition itself. Nothing more than that. Okay. But the most important thing I want you to remember is that 3 or 4 or 1.5, it is not in a regular scale. It is in logarithmic scale. It is an exponential scale. Okay. So what does that mean? So there is a solution here. It has got a pH of 6. Okay. There's another solution here. It's got a pH of 4. How many times this is higher? How many times is 6 higher than 4? It is not 6 by 4. It's not 6 by 4. Why? It's an exponential scale. 6 is 100 times more than 4 in exponential scale. Remember that. You are now looking at log scale, not a linear regular number system here, logarithmic scale. So when you see pH of 3 and 4, oh, it's just one number different. No, no, it's 10 times different. Something to keep in mind, logarithmic scale. Okay. The other confusing thing about pH is, as hydrogen or hydronium ion concentrations increase, pH decreases. So more acidic means more of hydronium ion concentrations. I'm sorry, yeah, acidic means more of hydronium concentration. So less pH means more hydronium concentration, more hydronium ion concentrations. Okay. So just few things to keep in mind. It's a negative logarithm. You can now, if you know the concentration of hydronium ion, you can calculate pH, but most important thing, I want you to remember, it is an exponential scale. It is in logarithmic scale, not a regular number system. So a small change in pH may mean several scales higher or lower. Big number, that's a big number. Let's see if I've forgotten anything here. I think I covered all of that. Let's go and really talk about pH, because now you see this graph, this picture I've shown you before, right? Urea, ammonium nitrate, it can be taken by plants, it can be interconverted. Now I'm using that same graph. Let's say if plants take a lot of ammonium or urea, lot of ammoniacal form of nitrogen, what is the charge of that? Positive charge. So inside the roots, positive charges are building up because it's taking a lot of ammoniacal form. It has to make some balance inside the cells. So in order to get the ionic balance, what the root does? It throws out H plus into the solution. What happens when H plus, more H plus is there in the solution? pH decreases. See, the plant is modifying pH. If you supply a lot of nitrates, negatively charged, the plant throws out OH minus out. When OH minus is out, the pH becomes higher. It becomes basic. So the plant can modify pH. It depends on the type of fertilizer you are supplying. Okay, remember that.
Sir, I had a query. In the previous slide, we discussed about pH scale. Is it from 0 to 14 or 1 to
It's usually from, you can do, it's usually from 1 to 14. The point is this, the point is when you get to those low values or really high values, it's theoretically impossible to have such a small hydronium concentration or such a large hydronium concentration. Okay, you can even go more than 14 or 15, but that is not theoretically possible. For our convenience, we put it in a small range. By the way, pH originally was discovered not for plants, not for anything. It was more for, you know, in Denmark, Scandinavia, they were producing beer, and they wanted to make sure that they maintain optimum pH. Otherwise, fermentation doesn't happen. So that's where they kind of describe this, and they developed that range, and we are simply borrowing that range and using it. Okay, but you don't want to be the ideal pH, by the way, because you asked this question for plants, and next slide is there for that. But the ideal pH for plants is 5.5 to 6.2. That's 6.5. That's it. You want to stay in that range. And I'll show you what happens. But look at this. Here are different types of fertilizers. And what are they? Are they acidic fertilizers, neutral fertilizers, or basic fertilizers? Look at some of the things that you commonly know. Urea, diammonium phosphate. It's got ammoniacal form, plus they are acidic because they let H plus out and make the substrate more acidic. If you go down, calcium nitrate, nitrates, potassium nitrate, whenever you apply nitrates, minus. They make it basic, and there are also some neutral ones, good ones too. So if you are planning to manage pH during production, keep this in mind. pH is dynamic. It will change every day. Every day it will change every day. So it is important to measure every day. And if pH is going higher, becoming basic, you can probably apply a little bit of ammonical form of fertilizer, bring it down. If pH is becoming very, very basic, you probably can use nitrate type fertilizer, calcium nitrate type to bring it up. But sometimes with just fertilizer, it is not sufficient. We have to resort to some acid and things like that. I will talk about that 2 slides later. But this is how a fertilizer can affect the pH of the substrate or even solution. Choice of the fertilizer is important. Okay. All right, this is important slide, the most important slide for pH. What are you seeing? Who can interpret this? Take a look at it, deep look at this slide. Okay, what do you see at the top? You see a pH scale all the way from 4 to 8. Okay, and then you have different elements here that you know. The wider the bar, the more availability in that range. So what are you finding? Let's talk about micronutrients first. Let me finish this first and you can ask me the question. Give me 2 minutes. Let's look at micronutrients.
Higher at lower pH.
They are highly available in lower pH, but if your pH is beyond 6.57, even you apply them in your fertilizer solution, they are not becoming available to plants. See, this is exactly why pH is important. You applied it, but they are not soluble. They got absorbed to substrates. In hydroponics, you know, they get either precipitated, and once they get precipitated, it's over. They are a new compound now. Or sometimes they even get attached to the tank, you know, those molecules. So it's very, very important to maintain pH. But now look at other things, calcium and magnesium, kind of more in the basic range. Nitrogen is available throughout. Why? Because
Different forms of nitrogen.
2 forms, isn't it? Ammonical and nitrate. So if your fertilizer got both of them, something is going to be available in one of those pH ranges, right? But we are interested in making sure that all these elements are available to plants, not 1 or 2. And we have to come up with a range that is suitable, or the range where most of the elements are in general reasonably available, and that range is what? That blue bar, the green bar color, 5.5 to 6.5. So this is important. Remember that range. Remember that range. Now, you may say, sir, I'm going blueberries and I want a lower pH. Yeah, of course, there are crops that may need even less than 5.5, but that's very specific. For most of the crops, that is the range, 5.5 to 6.5. 6.2, okay? 6.5 is okay. I have seen in many lettuce trials and spinach trials, they actually can do also even well up to 7, but there is always something on the fringes, right? This is the rule of thumb, 5.5 to 6.2. As long as you maintain that solution pH. So how do you measure pH? You need a sensor. So here is why that pH sensor and EC sensor are important. Otherwise, you are operating in blind. You don't know what is your pH, what is your EC. Somebody said apply this much fertilizer in this much tank and supply to plants. That is not the technology that you use in greenhouses. In greenhouses, you have to measure. You need data. You need to see your own data, not someone else's thing. If you can't do all of this, don't even enter into this business. You will, within 1 year, you'll see failure because you don't know what you are doing, basically. If you don't know what you are doing to your plants, why do you want to even do that? That's the point here. You need to buy these sensors, light sensor, temperature sensors, EC, pH sensors, make regular measurements, calibrate them, because it's all technology driven subject. This gives you a lot more crop, it gives you a lot more productivity only when you provide that optimum environment. It's not like every year I'm going to apply this much fertilizer on the soil and this business. What I've been doing for the last 10 years, it's good for me. No. You need to know pH changes every day. And once you change the pH from here to here, you see yesterday somebody brought some samples with intervenal chlorosis. I think somebody brought, right? Intervenal chlorosis is coming from some of these micronutrients, and that could be pH related. So knowing is important. Knowledge is power. Knowledge in your hand is the best power you can actually have. All right, let's keep moving. Couple of more slides. So let's say your soil is acidic. Let's say you're using peat. What is peat? Peat is acidic. Cocoa peat is acidic. You call it cocoa peat as peat here. I thought cocoa peat is coir, but maybe I'm wrong. Cocoa peat is okay. So let's talk about peat. No, sphagnum peat moss. Peat. Okay, that is acidic, right? I've shown you it's acidic, right? For that you add what? No. To manage, what is the other inorganic component you add to peat? Vermiculite. Vermiculite, right? You have to apply vermiculite because vermiculite is alkaline. Peat is acidic. So you kind of get neutrality there. But let's say you have a problem where you have a lot of acidic nature. So one way to do that is adding calcium carbonate, lime. Okay. What happens is when you apply calcium carbonate, simply calcium is going to replace this H plus. This H plus is why the substrate is low in pH. There's a lot of hydronium ions and they're going to get into the water and make it always low in pH. What we need to do is get rid of that and replace those spots on the substrate with calcium, and that's what is happening here. And that H plus comes into water and carbon dioxide evaporates, so you end up with water is lost, you end up with a substrate with Ca2 plus more, and that's how the pH goes up when you apply lime to the substrate. Okay, that's why pH goes up. This is the last slide. In the previous slide, I've showed you how we increase pH, right? Adding lime and then bring it higher. But you may end up with a scenario where your pH is actually higher. In this case, you have to bring it down. So the previous slide, your pH is low, you're trying to take it higher. But here is a scenario where you generally have a higher pH and you want to bring it down to that range of 6.5. So common practice in greenhouse industry is use acid, right? Acid has low pH. So what we do is we take, especially in big facilities, 1 acre, 2 acre, 5 acre greenhouses, we actually apply sulfuric acid. Tiny amount of sulfuric acid is injected into your fertigation system. Dosing, it's called dosing. You add it, and that lowers the pH of your fertilizer solution. Okay. Sulfuric. The reason why we recommend sulfuric acid is we recommend sulfuric only for large scale operations because it's the cheapest form of acid. If you go for phosphoric acid, citric acid, all of this, it's going to cost you. So sulfuric acid is a common practice. You add it to your inline fertilizer solution and the pH is brought down because of that acid application, and then normal pH solution goes to the plants. But it's small amount. But here is the problem with that sulfuric acid addition. So look at this graph. You have two farmers. One farmer's situation is shown in black color. The other farmer's situation is shown in orange color. All right. Both of them have high pH. See this dashed line is the pH that we want to maintain. But both of them ended up with what? Really high pH. They have to bring the pH down. How do they do that? They add sulfuric acid. But what is happening here is their acid requirement to bring from this pH to that pH, the acid requirement is this much for the first farmer. But for the second farmer, the acid requirement is even more. Why is this happening? This happens if your water is having a lot of those bicarbonates. Hard water. If your water is hard water, this is called alkalinity. Alkalinity is a measure of hardness of water. It is coming from bicarbonates that are dissolved in the water, and if our water has more bicarbonates, you require more acid to bring the pH from a level 1 to that optimum level than another farmer whose alkalinity is lower. He actually uses less acid. So alkalinity can affect the acid requirement. That's all I'm trying to say in this slide. Okay.
It can be correlated with the EC and alkalinity of water.
Alkalinity comes with because yes, of course, more alkalinity means more bicarbonates. Therefore, it's going to affect EC, but it is coming from what? Non-fertilizer ions. So if you have problem with alkalinity, either you have to deal with it or you have to make some adjustments. You have to make sure that you measure the level of alkalinity, its effect on EC. So you have to add on a little bit more fertilizer to make sure that you are supplying proper amount of nutrients. You probably have to throw away after some time. Don't want to continuously recirculate it. It's going to accumulate with time, but it's also going to affect your acid requirement. These are the problems with having water with high alkalinity. All right. Okay, I think that's the last slide. I can finish the next chapter, but I just need a couple of minutes. I want you to stay here, don't go away, but just take a break because we don't have time after 11 o'clock. But the next chapter is very easy. EC and PC is very, very important. That's why I spent some time emphasis on that, explaining the concepts deeper because it's pretty applied. This is what affects plant growth in general. Nutritional problems are the number one problem in greenhouse, and they come because people don't understand these concepts, EC and pH. They don't measure, they don't maintain, they don't know what they're applying, and then they end up with all deficiencies, symptoms that you saw yesterday. Okay, but the next chapter is slightly different. It's more on floriculture. Maybe it interests you more. Plant growth regulation, plant growth control. How can you make a plant longer or a shorter? How can you make plant flower more or abort the plant and keep it vegetative? All that stuff. Okay, but it's simple chapter. We'll go through that. Just give me a minute. I'll have a cup of water.